Welcome to the Lorium Technology OpenEvo Methodology Workshop. I'm Steve Phillips, Master Craftsman and Lead Designer for the FPGA on the Evo M51. Today we're going to go through prerequisites of this workshop, and then we're going to take a look at the two libraries that form the basis for our OpenEvo methodology, the Evo BSP and the Evo build template. Then we're going to take a deep dive into the architecture of the FPGA so we can understand the board support package, or BSP, and how we can integrate other logic into that inside of the FPGA. And finally, we're going to go through an example called the Evo PMUX CSR to see how we integrate this stuff in practice. The prerequisites for today's workshop include the completion of the OpenEvo Quickstart workshop. This means that we know that you already have an OpenEvo board, that you can talk to it and run sketches on it, and that you've already gone through the compilation process with Quartus. We're going to assume that you're familiar with Verilog HDL and with FPGA design in general, and specifically with the Intel Quartus tools. And when we say familiar, we mean we're not going to be teaching you how to code in Verilog or how to run the tool set. We're going to assume that you already have that basic knowledge and we can just build on top of that. For tools, we're going to need the Arduino IDE and the Intel Quartus Lite Edition version 17.1. Now, there are newer versions than 17.1, but a lot of our IP blocks are targeted at 17.1, so it's in general easier if you have that version than if you went to a newer version. Finally, you're going to need to have an M51 board and a USB cable. Just to recap what we should already have done in the Quickstart, we should have our SAMD board package installed using the Boards Manager, and we should have installed our Evo BSP and Evo build template libraries using the Library Manager. In addition, you may want to install the Evo PMUX CSR as our example if you want to try to follow along with that. So let's dive into our libraries and see what's inside of those before we look at the FPGA. Libraries have to adhere to the Arduino IDE specifications so that the Arduino tool can deal with them in a consistent way. That enforces a certain directory structure. There's some mandatory things, such as the source directory, which must include at least one .h file. There's a library.properties file and a keywords.txt file that have to be there because the GUI uses those to tell the user what those libraries are. But then there's some optional things, such as an examples directory or an extras directory. In our case, we're going to use the extras directory as the place where we store all of our OpenEvo related files. So let's take a look at those extras directories. First, for the Evo build template, inside of extras we have a Quartus directory where we store all of our Quartus related files. First off, we have the evo.qpf file, which is the project file. That's read in initially and kicks off the process. The evo m51.qsf is a Quartus settings file. This is the top level Quartus settings files that basically calls all the other ones. The OpenEvo.qsf is a Quartus settings file that the user can modify to add their own Quartus settings to and to specify any additional source files that they've added. Evo.cof is used to convert from an SOF format into the RDP format. Then we have a couple of TICO files. The Evo convert image takes that RDP format and converts it into the Evo image format that we use when we load it into the FPGA. And the Evo flashload.tcl file is the file that causes the Evo image file to get loaded through the SAMD into the FPGA. There's also a design directory under extras. Here we have the files that we need for the user to modify in order to add custom functionality to the design. So the Evo xb.sv is the top level of the user XB area. And there we instantiate our custom logic along with some other things that are already there, such as the Evo XB info module, which is already instantiated in there. In addition, we have an Evo XB address package. This is where the user can specify addresses for any CSRs that they add to the design. In the Evo BSP extras directory, we also have a Quartus directory. The first one on our list is the factory SOF file. This is the image that we load in at the factory before we ship the boards. We also have our bsp.qxp file. This is a compiled IP block that contains all of our board support package in one file so that it's easy to include into the image as we build it. The info.qsf contains the information about that BSP that's going to get loaded when we do the compile. And the Evo common.qsf is the bulk of all the Quartus settings files that are used common across any OpenEvo implementation. There's also a design directory. Here we have all the other source codes that you need besides what's in the BSP QXP file. So we have some packages here. The address package contains the CSR addresses for CSRs that are in the BSP. The BSP package contains the structures and other parameters that are used inside the BSP. The constants package defines some parameter constants that can be used anywhere in the design. Then we have some source code for Verilog. Here we have our clock reset module. That is a wrapper around the PLL, and it generates the resets, the clocks, and the enable signals that we need in our design. The Evo XB PMUX.sv file is our PMUX logic that's actually instantiated inside of the Evo XB file, and this allows multiple user blocks to share control of pins. We have a couple of top-level files, the Evo Core and the Evo Top files. These actually instantiate all the blocks that we see here. And finally, we have some IP blocks in IP directory and some miscellaneous other Verilog files that are used in the design. Here we see the steps of our methodology. First thing we're going to do is copy the Evo build template and call it Evo build. Then we'll take our new custom RTL sources and copy them into the extras design directory there, and then instantiate those into the Evo XB. Once we've done that, we can modify the XB address package to specify the addresses we're going to use for our custom CSRs. And then we're going to modify the XB info file to add any additional info registers that we wish to have. Once we've done all that, we'll go over to the Quartus OpenEvo.qsf file and specify all those new files we added and any other Quartus settings that we want to do. Once that's complete, we can now launch Quartus, load our project file, and compile the design, much as we did in the Quickstart. And once we have a clean design build, we can run our Evo flash load program to load that new image into our FPGA. So let's take a look inside the FPGA and get a better understanding of the structure inside of it. Here we see a very high-level block diagram of the FPGA. At the top in this white area is the Evo XB, which is all the customizable logic that we have. The gray area at the bottom is the board support package, or BSP. This includes a number of ports. We have the F port and the Z port, or Z bus, that connect to the SAMD, allowing the SAMD to talk to the ports on the FPGA. On this side, we have the D port, the E port, and the G port, which connect to the vias and castellated vias on the board, allowing the FPGA to control the values on those pins. We have an I2C block that talks to the SAMD, and the SAMD can then talk through that I2C to the CSR fabric and query and control all the CSRs in the design, including custom CSRs that are in the Evo XB. Lastly, we have a flash control module that is a wrapper around the flash logic. It allows us to write data from the SAMD through the I2C and into the flash itself. I'm going to note that this is not exactly drawn to scale. This white area at the top is a bigger portion than we show here. The BSP takes up about 20 to 25% of the FPGA, so you really have about 75% of it left to do custom logic. Let's take a little bit closer dive into the port logic. Each pin can be controlled either by the CSRs that are in the port itself or by control signals coming from the Evo XB, specifically from the PMUX logic in the Evo XB. For each pin, there are 3 signals that come across from the Evo XB: the direction, the out, and the enable. As you can see, the enable controls these 2 muxes, which select between the control coming from the PMUX and the control that comes from the local CSRs. So if we've got the enable set, we're going to choose the PMUX out and the PMUX dir, and then those will control this tri-state buffer that then controls the pin. Likewise, if enable is a 0, then the values coming from the local CSR registers will then control the tri-state buffer and the pin. We also take a copy of the pin, run it through a synchronizer, and pass it back to the Evo XB module so that the user logic can see the state of the pins. Going up one level in the hierarchy, we have the Evo GPIO block. In this block, we instantiate an Evo port module, 1 per each port of the design. So there's 5 of them. So each of those 5 instantiations gets a copy of the Avalon CSR bus. Each of them gets a dir, an out, and an enable bus coming in from the Evo XB area. And each has a set of signals going up to control the pins themselves. Also, we send a copy of those pins up to the Evo XB. Moving over to the Evo XB, we have instantiated an Evo XB PMUX module there, which allows us to share control of the pins amongst multiple IP blocks or XB blocks that are in the Evo XB. This diagram is a little more complicated than I'm going to get into, but I'm going to note that you can change the value of M, or the number of MUX inputs, based on the number of IP blocks or XB blocks that you want to be able to control a particular pin. And that will automatically make those MUXes and buses wider to allow more controlling. But you can see that in general, the enables come in and are used then to control the MUXes. So that setting an enable bit here will cause the corresponding dir and out values to be passed over to the ports themselves. We also OR all the enables together and send that over as the enable bit to the port. Now, one note here is that we assume that there's only one enable bit set at a time for a particular pin. If you have more than one enable bit set, that's going to cause conflict in the muxing logic. So in general, what we recommend is when you're moving from one block controlling the pin to another block, you first want to disable the first block so that none of the enables are set, and then turn on the second one so that it can control. And that way you won't have any conflicts between those enables. And the way we handle this coming in is that we basically, if there's multiple blocks that are controlling it, they are concatenated together into one wider bus, and then those bits are selected based on their position in that wider bus. And that's really what this math is amounting to here in the buses that you see. Going one level up from that, there's 5 instantiations of that PMUX logic in the Evo XB PMUX, 1 for each port. So there's 1 for port D, E, F, G, and Z. So if we look at our diagram, we can see that there are buses of some width coming in for each of those, and then a bus of a single width coming out that's going over to the ports themselves. And on the left side here with these buses, that's coming from the IP blocks themselves that are trying to control those pins. So going up to the top level again, or the core level, and a little bit more detail of our block diagram this time, we can see that the gray boxes are the blocks that are provided by Alorium as part of the BSP or associated logic. The white blocks, for instance, these user XB blocks, those are just example implementations that might be implemented by somebody in a design. So in the Evo BSP, we see we have our GPIO block with 5 instantiations of the port logic. There's the Evo Flash, which has the flash logic within it. And there's the Evo I2C. Now the I2C is the master on the CSR bus. And you can see that that bus then goes to all the other blocks in the BSP and also over to the Evo XB, where it connects to the info block as well as any other user custom logic that wants to be on that bus. The Evo clock reset block is outside of the BSP and is a wrapper around the PLL. It sends clocks and resets to all the other logic. In the Evo XB itself, we have our XB PMUX logic. Here we can see our 5 instantiations of PMUX, and we can see that we have our user XBs connected to that, in some cases multiple connections to a single, like here we have port E, which has 2 blocks trying to control it. And also the Evo XB info block is inside of the XB. So now we understand a little bit better how the chip is put together and where the custom logic goes within there. Let's look into our example and see how that works. So normally you would take your Evo build template and copy that to Evo build and then add your files to it. In this case, we have a canned example, so I'm going to copy that into place as Evo build, and we'll look at the files there to see how we've modified them. We already have our RTL sources copied into that, and we have already modified the Evo XB, but we'll take a look at what was done there so that it's easy to understand what happened. So first let's look at the Evo PMUX CSR and what's inside of that library as our example design. There's a Quartus directory, and the same set of files that we have in the Evo build template exist in here. We haven't changed any of those except for the OpenEvo.qsf file, and we'll see that in a little bit. In the design directory, we have the same set of source files, but we've added one additional one, the Evo PMUX CSR block, which is the custom logic that we've added. So let's take a look at the Evo PMUX CSR source code itself. This module was developed to test the PMUX logic, so it's got some complexity to it that we probably normally wouldn't have for an example. But we can take a look at it and just look at parts of it. For instance, we're going to see how we create CSRs, the registers themselves, and we're going to see how we connect up the CSR bus as a slave. And then we're going to see how we're going to take those CSRs that we've created and wire them up so that they connect to the PMUX module. So at this point, I'm going to escape out of my presentation and bring up my source editor. And here we see the Evo PMUX CSR module. Right at the top, we have instantiation parameters that are defined, and you can see we have several addresses defined and initially set to 0. The final values for those will be set when we instantiate this, and those values come from the Evo XB address package. For I/O in the module, we have our PMUX triplet of dir, out, and enable. Those are going to the PMUX module. And we have our pin values coming in as PMUX in. We also have our CSR slave connection. Now, taking a little bit closer look at the CSR slave logic. This is a templated set of logic that is similar in all slave connections. So let's take a look at what we do here. For each of the CSRs that exist, we create the CSR by defining a logic flip-flop or register. And then we also create a select, a write enable, and a read enable for each of the CSRs. So we've got all these CSRs defined. Each of them has a select, write enable, and read enable. You'll note here also that for the dir, out, and enable triplets, those are actually register files. So they are a 2-dimensional array rather than a single dimension array. And there's multiple entries in each of those. Once we've created those pieces of logic, we're going to assign values to them. These selects are created by comparing the incoming address with the parameter address that's assigned to that particular CSR. So if there's a match there, it's going to set the corresponding select bit. Then we're going to use those select bits in association with the write signal to create write enables, and with the read to create read enables. So now for each of those, we've got values for the select, write enable, and read enable. So now we're ready to control our registers. For example, we have the control CSR. It is set to zeros when we have a reset. When we have a write enable, it's going to load data off of the write data bus. And otherwise, we're going to set it to 0. Similarly, for the status, we set it to 0 and we read data off the write data bus. Then for the register files for dir, out, and enable, we first create a write pointer CSR. And this is used to specify which entry in those register files we want to address. So looking at the register files themselves, if we have a reset, we're going to walk through all the entries in the register file and set them to 0. If we have a write enable, we're going to use that write pointer value to read data off of the write data bus and stick it into the appropriate entry in the register file. And then we've got some other features here for use in that verification process that I mentioned. But we'll see here that the dir, the out, and the enable have very similar logic since they're all very similar register files. We also have a CSR for the in, just capturing the values off the pins. For the output signals of the CSR bus, we're simply ORing together values coming from those CSRs. So for the read data coming back, we're capturing the value of those CSRs and just using our select bits to select the one that we want. You'll notice for dir, out, and enable, we're using the write pointer again to specify which entry in those that we're going to send back. So it's really a read pointer, but we'll just use a single pointer to handle it. And then for the read data valid, we're simply ORing together all the read enables. There should only be one set. The wait request is always a 0 in our CSR implementation, so we just tie that off here. Finally, we have the assignments to the PMUX buses. So we're not talking about the CSR bus anymore, we're talking about the PMUX outputs. And what we're going to do here is we're going to essentially take each of the entries in the register file and concatenate them together. So we have one big wide bus that has all of those entries in a single bus. And those will just come out of this module and then go into the PMUX module on the Evo XP. So let's take a look at the Evo XB. This is a custom or standard wrapper around all the custom logic. And it contains standard an IO list that provides all the signals we can from the BSP and the clock module to come into the Evo XB. Every single instance of this will instantiate the Evo XB PMUX module and the Evo XB info module as standard. And then any other additional custom logic you want to add. In our case, we're going to add in 5 copies of the Evo PMUX CSR, 1 for each port. The top of this file contains a bunch of comments that describe what's in the file. Of particular interest is this description of the CSR bus that shows the waveforms. This allows you to see how that CSR bus actually operates. Essentially, writes happen in 1 clock and reads have a 1 cycle delay. For I/O, we have all these signals coming from the clock, which all the clocks we're generating, the resets we're generating, and the enable bits that we're generating. We also have going out to each port a set of, as I call them, a triplet dir, out, enable to each port of the control signals, and also coming back the copy of the input signals. And finally, we have our slave interface. For each of the modules that are instantiated that are connected to the CSR bus, we're going to create read data valid, write request, and read data signals for those. And then you'll see here that we simply OR those all together coming from those blocks to create the version that goes out of the Evo XB over to the BSP. Since we're just using a wire OR in this case, we want to make sure that if we're not actively trying to use those output signals, that we set them to zeros inside of our custom logic. ORing together zeros gives you zeros. If any of them are set, it's going to set that bit. So we want to make sure that everything's zero unless we actually want to force a 1 there. First thing we're going to do is instantiate our Evo XB info block. And this simply has a CSR slave interface on it. Then we're going to instantiate our XB PMUX module. First thing we have here is a PMUX width defined for each of the ports. By default, these values are set to 1, but in this case, we're going to set it to 4 because we want to allow up to 4 different blocks to set values on a per pin basis. What you want to do is take a look at your port and all the pins in the port, and whichever one has the most different IP blocks or XBs that are trying to control it, you'll set that as your value. So for other pins in that same port that don't need that many controllers, they'll have some extra busing coming in, but this is a simpler way of doing than trying to do it on a per pin basis. We're doing it on a per port basis. Then what we're going to have for each of those is we have a set of signals that connect those custom blocks to the PMUX block. So in this case, we've got 5 different sets of those coming in. Here, commented out is the default setting for those you will find in the default version of this file. Finally, we instantiate the XB PMUX module. We're feeding into it our parameter values for the widths, which will then be used internally for each of those instantiations inside. And we're feeding in our signals coming from the custom logic. And coming out of it, we have our control signals that are then going to go over to the BSP and the ports. Finally, we see instantiations of our custom logic. The Evo PMUX CSR. There's 5 different copies of this in the Evo XB. Let's take a look at the first one, which is for port D. You can see here we're feeding in our addresses for port D, PMUX D. So these are all specifically for port D. And those will then be used as the addresses for the CSRs in that instantiation. We can see we've got our PMUX dir out enable signals coming out. Those are going to go to the PMUX module inside the Evo XB. And coming in, we've got a copy of our pin values, PMUX in. We've also got this slave connection to the CSR bus. And there are 5 copies of this, 1 for each port. Next, we're going to modify our Evo XB address package to specify the addresses we're using. This file allows us to set addresses based on what we've defined in our custom logic. First thing I will note in this file is that you should use addresses greater than 800 hex. All the addresses up to 800 are used in the BSP, and so we shouldn't be using those in the Evo XB area. So you'll see, as I define here, addresses for all of the CSRs in our PMUX CSR logic. They start at 911 and go up from there, so they're over 800. But I've got addresses defined for each of the instantiations, 1 for each port. They all have unique addresses. Next, let's look at our XB info module. The Evo XB info module allows you to specify values for the info registers and even add additional info registers if you like. So taking a look at the code, we can see at the top here we're defining parameters. What we do is use parameter pairs of an address and a value to specify each of the info registers. We do this because the info register is an indirect address register. What you do to access it is you write an address to it and then read the info register back, and you will get the value that you've addressed. So for instance, the info number is at address 0. So you would write a 0 to the info register, and then when you read the info register back, you'll get the value specified by the info num val, which in this case is a 3. These that you see here are the standard ones we include in every instantiation. The number address val pair is used to specify how many additional CSR registers are available in the info register. So you can add additional info registers just by adding additional address value pairs here in the parameter list. But any you would add will increase the number that you should have in the number value field. The standard ones we include are the vendor, the model, and the type. Vendor we set to ALO, which is our tag. Model we set to Evo, and type we set to PMUX because that's the particular implementation I'm doing. Now, if you were going to put this in some other thing and you wanted to call it something other than Alorium Evo PMUX, you could change it to whatever you like. You can also add more address value pairs here, and they don't have to be in ASCII format. You can enter things in as integers in either decimal or hex format. You should note if you're entering ASCII, as I'm doing here, you're limited to 4 characters per value because it's a 32-bit value in the parameter. Then for each of those pairs that you've added, you'll want to add a new entry in this case statement. You can see here that if we are addressing the number address as the address we're reading from, it will return the num value, etc. So any additional ones you add, you'll want to add an entry into this case statement corresponding to the address that you've added and the value that you've added. Now that we've modified all of our design files, let's go over to the Quartus directory, and we need to modify our OpenEvo.qsf file. This file is usually used just to specify any additional source files that we've added. And here you see in this case, I've only added a single statement that just specifies the Evo PMUX CSR.sv file that I've added over in the design directory. So now we've modified all our design files and we've modified our QSF file. Now we're ready to go ahead and compile. So what you want to do is go into the Evo build, extras, Quartus, and double click on the evo.qpf file. This is the same process that we went through in the Quickstart. So what you'll do then is compile it by hitting the compile button. And if it compiles cleanly, then we'll go ahead and run our Evo flash load program, same way we did in the Quickstart, to load that image to the FPGA. Now it could be, or maybe even is likely, that you're going to run into compile problems the first couple times you try to run it. So you'll have to take a look at any errors that pop up, go back to your source code, make changes as required, and iterate back to the compile. Iterate through until you get a clean compile, and then you'll be able to load your FPGA image. So that concludes our workshop on the Evo methodology. Hope you've enjoyed this. For more information, you should visit our website at aloriumtech.com or visit our YouTube channel, where Jason has uploaded many great videos that go into more depth on a variety of different topics, more examples, more cool things you can do with the Accelerate and the Evo. And if you have any technical questions, you can reach us using our email support@aloriumtech.com. I hope you enjoyed this webinar, and I hope you're having a great time with your Evo M51. If you do anything really cool with it, please let us know. We'd love to hear about it.